So welcome to experiment third that we are going to perform on DC shunt motor. So we are going to perform the no load test and load test and speed control of DC shunt motor. So first we will perform the no load test and then we will go for load test and then we will perform the speed control test on DC shunt motor. So what are the objectives for the no load test? So it is basically the Swinburne's test, what we can say. So predetermine the efficiency of a DC shunt machine when run both as a generator and a motor. So the same machine will be running as a generator or a motor, and then we have to determine the efficiency under no load condition. The machine is a DC shunt machine. DC shunt machine means the field winding is connected in parallel with the armature. So this is basically the Swinburne's test. So let us see the nameplate details first. So for a DC motor, the power rating is 3.5 kilowatt, voltage is 220 volt, maximum current is 18.6 ampere, the rated speed is 1500 rpm, excitation current is 0.95 ampere, and the winding type is shunt, whereas the armature resistance is 1 ohms and the shunt field resistance is 174 ohm and brake drum radius is 0.1. Now, apparatus required, we have the voltmeter, ammeter, rheostat and tachometer. So two different rheostat we will be using. One is of 360 ohms, another is of 145 ohm, and voltmeter 300 voltmeter, digital one. So all voltmeters and ammeters will be digital and rheostat will be coil type. Okay, so ammeter maximum current is for the motor is 18.6, so we are going a ammeter with 20 ampere, and we use a tachometer to measure the speed up to 2000 rpm. Since 1500 rpm is the maximum speed, so 2000 rpm tachometer will suit our job. Now here in the DC shunt motor, let us see under the no load condition how the diagram will be there. So we see the motor, this is the armature of the motor and this is the field winding. So in order to measure the field current, we have connected an ammeter, and through a rheostat we can vary the field current. So we have a 3-point starter. The starter is used to limit the starting current because to the motor, because the motor has the tendency to draw a huge amount of current at the starting, hence starter is used. Now we have three terminals, line, field and armature. So armature terminal will be connected to the armature of the motor, the field terminal will be connected to the field of the winding, and the line terminal goes to the supply end. So basically we give a DC supply, that is 220 volt DC supply, and we have an ammeter and voltmeter. Voltmeter will always be connected in parallel and ammeter will be always connected in series. So voltmeter measure the supply voltage and this ammeter measure the supply current. This ammeter will measure the field current, and since there is under no load, we are not connecting any load. Now we know that the efficiency is given by power output by power input, whereas power output can be written as power input minus losses and divided by power input. So we have to calculate the efficiency of the DC motor under the condition when it is under the no load and as well as the load. So various losses taking place in DC motor and efficiency can be calculated by carrying out the test on DC motors. They are different method of testing of DC motors, and these methods can be classified as direct method and indirect method. So in order to calculate the efficiency, we can follow different methods. One is known as direct method, another is known as indirect method. In direct method, we will be putting a direct load and then measure the losses to calculate the efficiency. In the indirect method, we do not put any load and then we calculate the efficiency. So basically in this particular test, we'll go for indirect method of testing where the motor is not loaded directly, but the losses and efficiency at different load can be estimated or predetermined. So one of the two different methods available for testing for DC motors are the Swinburne's test or the Hopkinson test, and commonly used in practice for shunt motor. So Hopkinson test we have already done in experiment number 2. Now experiment number 3, whatever we are going to follow, we'll discuss our Swinburne's test. So Swinburne's test is basically a no-load test that is performed on a DC machine, and thus it is an indirect method of testing in a DC machine in which flux remains practically constant. Since we know that in a shunt machine the flux will remain constant, hence we are performing on the shunt machine. So machine is started and run as a motor. So machine will be started and run as a motor with shaft decoupled from any load. So since load is not there and it is decoupled, it is under the no load condition at the rated voltage and the rated speed. So rated speed is 1500 rpm and rated voltage is 220 volt. We are performing this test. So at the starting, some resistance is connected in series with armature, which is cut when the motor attains sufficient speed. So we need to add some resistance at the starting so that the motor do not draws a heavy current, and then as the motor gathers speed, it is basically a process to cut down the resistance. Now the speed of the motor is adjusted to the rated speed with the help of shunt field rheostat. Then the rheostat which is connected with the field will be useful in controlling the speed of the motor which is maintained at the rated speed. So without actually loading the motor, the losses and efficiency at different load condition can be determined, and the test is very easy to carry out of a machine of any size, particularly convenient for large machine. So for a large machine, if you put a large load, then losses will be quite high. So in order to reduce these losses, the test is being performed on the no load test. So the losses that will be there in the DC machine is basically the copper loss, the iron or the core loss, and the mechanical loss. So these losses we are going to determine. So here it is the actual panel. We can see that there is a motor which is where the field winding is connected in parallel with the armature of the machine. So it is basically a DC shunt motor, and all the digital panels are there which are used to measure the voltage and the current, and here we have an MCB which is used to turn on the supply. So here we have a starter which limits the starting current by twisting and turning this starter point to add up the resistance. So we have a rheostat. This will be used to control the field current by varying its resistance, and we have a motor which is basically a DC shunt motor. We have an external load which is connected, that we will see later how the load is included, but first we will do the no load test. So some precautions we need to take: starter arm must be kept in the off position, motor field rheostat must be kept in the minimum resistance position, motor should be started and stopped under no load condition, and brake drum should be cooled with water when it is under load condition. So whenever the load is there, then you have to put a little amount of water so that the brake drum is cooled. So we see the connection for the no load test, then we'll perform the load test, and then we perform the speed control. So here, according to the connection given, we have to appropriately connect the circuit based on the circuit connection given, so that we can do the measurement. So perform the connection and then start the procedure. So connect the circuit, and then motor field rheostat must be kept in the minimum resistance position. So the field which is there for the motor you keep in the minimum position, then switch on the MCP and start the motor with the help of 3-point starter. So 3-point starter will limit the starting current, and you have to maintain the speed of 1500 rpm, which is the rated speed, by adjusting the rheostat. Now you have to note the reading for the voltmeter, ammeter, and the field current. You have to note down and bring the field rheostat to the initial position and switch off the MCB. So before switching off the supply, you have to bring the field rheostat at the initial position and measure the armature resistance of the DC shunt motor, which is basically given in the nameplate rating. So speed armature resistance is basically given in the nameplate rating, which you have to measure. Note down speed of the motor at rated speed is 1500 rpm, and then only one observation is sufficient for the no load test, that is what is the supply voltage, line current, and the field current. So three measurement, only one measurement under the three categories is sufficient for performing the no load test. Then you have to do the load test then. So in order to do the load test, you connect the load and when first you do the perform the test when the machine is running as a motor. In that case, for the different load, so load can be varied with the help of the current. So here up to 18 ampere current we can go, because the rated current is 18. So measure the voltage, measure the field current, measure do the calculations from this to here. So this is the calculation part of the table. So here you have do the calculation, and this is the measurement part. So here you have to measure it, and here you have to calculate. So measurement has to be done for different amount of the load. So load will be determined with the help of the current, which is the armature is drawing, and measure the voltage. So field current also you need to measure. Then armature current is basically load current minus field current. Now we are dealing with the motor. Then input power is equal to the voltage into load current. What is the copper loss you determine, I square R, and then the total loss, output power, and efficiency is output power by input power. So this particular end of the table is basically the calculation, and from here to here you will be doing the measurement. So when the motor is running as a generator, same up to this point you are basically doing the measurement. So you can measure up to 18 ampere, and then this part of the table is basically the calculation. So this part of the calculations we will be doing depending upon the formulas, whatever we know the formulas, and this is your measurement part. Okay, so we're measuring the voltage for the different amount of the load current, measure the field current, and then we know that when the machine is running as a generator, it will be load current plus field current. Output power we determine copper loss, total losses, input power, and efficiency is output by input. So we know that the motor input power is the sum of the rotational losses plus armature resistance loss. Okay, and then this is the loss we have. So rotational losses will be again, the friction and the windage losses, and you have the iron losses. Iron loss is basically the constant loss, friction and the windage loss is basically the variable losses, and you have the is square r, which is the variable loss. So you determine the different losses, some field loss and constant losses you have to determine. And when the machine is running as a motor and the machine running as a generator, use the appropriate formula to determine the machine input, armature current, copper loss, total loss, what is the output, and the efficiency. So we do these all type of measurement for, sorry, the calculation when the machine is running as a motor or a generator under the load condition. Okay, so we'll get a model graph. We plot the graph on efficiency on the y-axis. So on the y-axis efficiency, and on the x-axis you have armature current. So you should get a efficiency curve where the motor efficiency should be less than the generator efficiency. So this is for the efficiency of the generator, this is efficiency of the motor. So plot has to be drawn, motor efficiency versus output of the motor, and generator efficiency versus output of the generator, and write the calculation conclusions and interference from this experiment. Now what you do is that you connect a load test on a DC shunt motor. So in the previous case, for different value of armature current we have performed the test, but we have not connected the load directly. So in this we are connecting the load directly. So the previous experiment, if you see here, this is the variation of the armature current whatever we are doing. So this is the indirect method of testing, and here we are doing the direct method of testing by connecting a load to the motor. So motor shaft is connected with a brake drum, and two springs are there, S1 and S2, which can be helpful in maintaining the proper amount of load on the motor, and the remaining part of the circuit remains the same. Only difference is that you can connect the brake drum or the load to the armature of the motor. So this is the direct method. Direct method means you are putting the actual load on the motor, because in the previous method you have not put a load, you have just varied the armature current. So in this method the motor is put on the direct load by means of a belt and a pulley arrangement, and there is a tension of the belt to adjust the load and various values of current. So load is finally adjusted to give the full load current. So please do not exceed to do this experiment above the full load current. So if you see in the nameplate rating, you will get an 18 ampere as the full load current. So you should not exceed this full load current. So maximum measurement has to be there up to 18 ampere. So power developed gets wasted against the friction between the belt and the shaft due to braking action of the belt. The test is called the brake test. So since there is the rotating part, so obviously some amount of losses will be there due to friction, and since brake is applied, so it is known as the brake test. So here we can see that we have the load which is controlled with the two spring S1 and S2, which is connected directly to the panel of the DC shunt motor, and we are going to perform the load test. So all connections we will be doing given with the circuit connections given, and then follow the procedure that is given. Connect the circuit. Motor field rheostat must be kept in the minimum resistance position, which was same, and switch on the MCB and start the motor with the help of 3-point starter. Vary the field rheostat to maintain the speed of the motor at 1500 rpm, which is the rated speed, and then you can load the motor and note down the spring S1 and S2 and the load voltage and the load current, and remove the load on the motor to reach 0 before switching off. So this you have to do before switching off. The precaution: remove the load and bring the rheostat to the initial position and measure the effective diameter of the drum. So this is can be measured with the help of a tape. So here observation table for the load test, if you see, then you have to measure first the radius of the brake drum, you have to measure, then you have to measure the load voltage, load current, speed, and what is S1 and S2 showing in the spring. So up to this point you have to measure. So after this is the the calculation part of the calculation part, where if you have measured S1 and S2, you can easily calculate what is the difference S1 and S2. You calculate the torque, input power, output power, and then divide the input power by output power will give you the efficiency. So torque equation you can use as this equation: torque is equal to 9.81 S1 minus S2 into radius of the drum. Okay, and then the power input is equal to voltage into current, and output you can measure as 2 pi n T by 60, where T is the torque which you have calculated here, and n is the speed in rpm, and pi is 3.14. So you can calculate the efficiency as output by input. So these are basically the calculations you will be doing for the observation table. Then draw the graph of the efficiency versus output power, speed versus output power, and torque versus output. So three graphs you have to draw and three plots you have to obtain. So here you can see that efficiency graph, this is the torque graph, and this is the speed graph. So three graph you are getting for the output power with respect to the three different quantities. So write the conclusion and obtain the inference from the experiment. Third part of the experiment that we are going to perform is basically the speed control. So you have to control the speed of the DC shunt motor. So how do you control the speed of the DC shunt motor? So there are two different available methods. One is known as the armature control method, and other is known as the field control method. So if you know that speed is directly proportional to the back EMF by flux, and flux is proportional to the field current, so in order to control the speed, you can either control the armature voltage or you can control the flux by controlling the field current. So when you are controlling the armature voltage, that is EB, it is known as the armature control method. When you are controlling the field, here it is basically known as the field control method. So if you are adopting one method, the other item has to kept constant. That is, in armature control method, you keep the field current constant. If you are going by field control method, keep the armature voltage constant. So here in the speed control method, you can see that the circuit of the motor is same. You are connecting a voltmeter to measure the input voltage. This ammeter is measuring the field current of the field winding, and you have a resistance or a rheostat connected in series with the armature, because we want to vary the armature resistance or the armature current, and we measure the voltage across the armature. So we do this speed control of the shunt motor in easy control step, and then when the load is increased, the armature tend to slow down. This result in less back EMF. So what happens when you increase the load, then the motor will be slowing down and back EMF will be produced less. This account for less opposition against the supplied voltage. So the motor will draw more current. So when your load will be more, then the armature current drawn of the motor will be more, because the speed has reduced. So these increase the current result in torque to gain speed. Thus, even when the load increases, the net effect of load on speed in shunt motor is almost nil. So we know that the shunt motor is basically a constant flux motor or constant speed motor. So even the changing in the load is not affecting, because the armature current is controlling the torque, and then it is nil the DC motor speed. So with the load decreases, the same alternate happen, that armature gain speed and generate more back EMF. So polarity of back EMF is against the supply voltage, and load reduction result in less current, and hence speed is maintained constant. So either whether the load is increasing or decreasing, what will happen, that since it is a shunt motor, it is a constant flux motor or constant speed motor, it will just maintain the armature current with respect to the load and maintain the constant speed. So that is the reason we say that DC shunt motor are very suitable for constant load applications when belt driven, and it is constant speed motor for industrial applications. So DC shunt motor equations, you should be aware that the speed of the DC shunt motor, so we know that the speed of the DC shunt motor is equal to, some constant Kn into Va minus Ia Ra, which is the back EMF divided by the flux. So this equation is useful to know the controlling method of the speed. So we can control the armature voltage, controlling the armature current. So this armature current is controlled with the help of the rheostat, which is connected with the armature, and the flux is controlled with the help of a field current control, which is with a rheostat, which is connected in series with the field. So either there will be field control or armature control. So when you are having a field control, you keep the armature voltage constant. When you have armature control, you keep the field current constant. So these two methods we will be using to carry on the speed control, and then we will be using the method of flux control, which is known as the flux control method, and armature control, which is known as the rheostatic control method, because here you are connecting a rheostat in series with the armature. So in series with armature, so it is known as rheostatic control. So here you can see that there is a rheostat which is kept, and this is the variable portion of the rheostat, and this is the fixed portion. So here you have the fixed portion of the rheostat, this is the variable portion of the rheostat. This variable portion is moved so that the field current, armature current associated with the armature changes. So we do the connection as per the given in the circuit diagram, and then we will be follow the procedure of both armature control method and field control method, and then we will measure the data. So in armature control method, your field current has to be constant. So this has to be constant. You keep for a particular field current, you measure the armature voltage with respect to speed. And then in the field control method, you keep the armature voltage constant. So you keep the armature voltage constant and measure the field current with respect to speed, and then you draw the curve of the field control method and armature control method. You will see that you have a relation, speed is directly proportional to EV by phi. So if the armature voltage is increased, obviously the speed will increase. If the armature voltage is decreased, the speed will decrease. That is, it is directly proportional. Whereas speed and flux are inversely proportional. So if you increase the flux of the field current, the speed will decrease, and vice versa. So we have to draw the particular curve for the armature control method and field control method, and obtain the graph, and then you will be in a position to explain the result of speed characteristic of a DC shunt motor in armature control method and field control method, and some of the questions you should answer. What are the advantages and disadvantages of performing swing burst test? So swing burst test is basically the indirect test which we have performed. Okay, what is the difference in the performance characteristic efficiency versus output of a DC machine obtained in swing burst test and the load test? So load test is basically the direct testing, and third one is what is the 3-point starter and what are the advantage, and fourth one is which method is best suited for speed control and give few applications. So these are the questions that you should be able to answer after performing this test. So we are doing 3 tests in this particular experiment. One is no load test and speed control on a particular machine, that is a DC shunt motor. And the no load test is basically the indirect test. So no load is applied, it is the swing burst test, and load test is the direct test where we are applying the actual load. And speed control we are doing by two methods. One is armature control method, another is field control method. So this completes the third experiment. Please see the video tutorial to understand the connection and how do we take the observation. Thank you.